On the morning of October 10, 1957, Tom Hughes, the deputy reactor manager, peered through a thick glass inspection hole into the concrete belly of Windscale Pile number 1 and froze. He expected to see the dull, dark graphite of a cooling reactor. Instead, he stared into the mouth of a volcano. 4 fuel channels were glowing a terrifying, bright cherry red. The reactor was not just overheating, it was burning. For nearly 48 hours, Britain's first plutonium factory had been a ticking time bomb. Driven by a desperate secret Cold War mandate to build a hydrogen bomb, operators had pushed the primitive air-cooled machine beyond its limits, modifying it to produce tritium, a volatile task it was never designed for. Unknowingly, they had turned the cooling fans into bellows, fanning an 11-ton uranium fire that was now hot enough to melt steel and threatened to vomit a plume of cancer-causing poison across the United Kingdom and Europe. This report uncovers the true story of the Windscale fire, stripped of the official whitewash. It details the frantic, heroic battle led by Deputy Manager Tom Toohey, who stood atop the reactor shield, risking lethal radiation to stare down the fire and make the impossible decision to flood the core. It exposes the subsequent political cover-up by Prime Minister Harold Macmillan, who suppressed the damning Penny report to save the special relationship with the United States. It is a story of brilliance, hubris, and the terrifying thin line between a successful failure and a continental catastrophe.
To understand why Windscale Pile 1 burned in 1957, one must first understand the desperate circumstances of its creation in 1947. Emerging from World War II, the United Kingdom was a victor in name, but a debtor in reality. Its economy was shattered, its cities were scarred by the Blitz, and its status as a global superpower was rapidly eroding. During the war, British scientists had been integral to the Manhattan Project, the US-led effort to build the atomic bomb. The Tube Alloys Project, Britain's own nuclear program, had been merged with the American effort under the 1943 Quebec Agreement. British physicists like William Penny and John Cockcroft believed this collaboration would continue in the post-war era. However, the passage of the U.S. Atomic Energy Act of 1946, known as the McMahon Act, shattered this illusion. The act strictly prohibited the transfer of nuclear information to any foreign country, including allies. Britain was cut off. Overnight, the flow of technical data ceased. If the UK wished to maintain its first-class power status, it would have to build an atomic bomb alone from scratch and in total secrecy. As William Penny, who would later lead the inquiry into the fire, famously contended, the discriminative test for a first-class power is whether it has made an atomic bomb, and we have either got to pass the test or suffer a serious loss of prestige, both inside this country and internationally. The Labour government, under Prime Minister Clement Attlee, authorized the development of a British nuclear deterrent in January 1947. The timeline was aggressive. The goal was to have a plutonium bomb ready for testing by 1952. To achieve this, the Ministry of Supply needed plutonium production reactors immediately. The site chosen was a remote derelict Royal Ordnance Factory on the Cumbrian coast near the village of Seascale. It was known as Windscale. The location offered 2 essential assets: isolation from major population centers, unlike the alternative site at Risley, and access to the abundant, albeit soft, water of wastewater for cooling. The design of the reactors, or piles as they were then called, was dictated by speed and the lack of specific safety knowledge. The Americans had used water-cooled reactors at Hanford. However, water-cooled reactors required massive exclusion zones due to the risk of coolant loss and subsequent meltdown, land that the densely populated UK could not spare. Furthermore, the complex plumbing of a water-cooled system was deemed too time-consuming to engineer without American blueprints. Consequently, the British engineers opted for an air-cooled, graphite-moderated design. It was simpler, faster to build, and theoretically safer, or so it was thought. The Windscale piles would be massive once-through systems. Air would be sucked in, blown through the core, and blasted out a chimney. It was a primitive, brute-force approach to nuclear engineering. Construction began in 1947. The pace was frantic. Thousands of workers descended on the Cumbrian coast. The piles rose as two colossal concrete monoliths, 120 feet high, separated by a central processing plant. Even during construction, the culture of production over perfection was evident. In 1950, as Pile 1 neared completion, calculations from the Atomic Energy Research Establishment at Harwell suggested that the neutron flux, and thus plutonium production, would be lower than anticipated. To fix this without delaying the startup, the decision was made to reduce the amount of neutron-absorbing cladding on the fuel elements. This led to the first display of the can-do improvisation that would later define the fire response. Tom Toohey, then a young manager, set up a makeshift workshop on the charge hoist of the reactor itself. Over 3 weeks, in August and September 1950, he and his team manually trimmed a strip 1/16 of an inch wide from the cooling fins of 70,000 fuel cartridges. It was a monumental ad hoc effort that saved the schedule, but hinted at a willingness to alter specifications on the fly. By late 1950, the piles were operational. They were delivering plutonium. Britain detonated its first atomic bomb, Operation Hurricane, in 1952. Windscale had done its job, but the Cold War was evolving, and the piles were about to be pushed beyond their design limits. To understand the mechanics of the fire, one must visualize the physical reality of Windscale Pile 1. It was not a gleaming stainless steel power station like modern reactors. It was a factory, gritty, industrial, and deafeningly loud. At the heart of the building lay the biological shield, a massive concrete box protecting the staff from radiation. Inside this box was the moderator, a block of pure graphite, 50 feet wide, 50 feet high, and 25 feet deep, weighing nearly 2,000 tons. Drilled horizontally through this graphite block were over 3,000 fuel channels. The fuel consisted of aluminum canisters roughly the size of a soda can, containing a rod of natural uranium metal. These were loaded into the front of the reactor and, after irradiation, pushed out the back into a deep water channel where they fell into skips for cooling and subsequent chemical separation. The lungs of the reactor were the blower houses. Located on either side of the pile, these housed enormous diesel and electric fans that drew air from the outside atmosphere. The air was forced through the concrete biological shield into the graphite core over the hot fuel cans and out the back. The exhaust air, now heated and carrying argon-41, was channeled up a 400-foot chimney. The chimney was not merely a smokestack, it was a critical component of the cooling draft. One feature of the Windscale chimneys stood out, a large bulbous gallery at the very top. This was the filter gallery. During late construction, Sir John Cockcroft, the head of the research division, became concerned about the possibility of a fuel-cladding failure releasing uranium oxide dust. He had seen data from the U.S. Clinton pile that suggested such accidents were possible. He insisted that high-performance filters be installed on the chimneys. The engineering team was furious. The chimneys were already built. Installing filters at the top, rather than the bottom, required lifting heavy concrete beams and equipment 400 feet into the air. It was expensive, delayed the project, and was widely regarded as unnecessary paranoia. The filters were mockingly nicknamed Cockcroft's Folly. Cockcroft held his ground, leveraging his prestige as a Nobel laureate. The filters were installed. 7 years later, this folly would be the only thing standing between the UK and a continental-scale ecological catastrophe. By 1955, the strategic landscape had shifted. The Soviet Union had tested a hydrogen bomb. The US had the super. Britain needed a thermonuclear weapon. A hydrogen bomb requires tritium, a heavy isotope of hydrogen. Tritium does not exist in nature. It must be manufactured by bombarding lithium with neutrons. The Windscale piles were not designed for this. However, the government ordered that they be modified to produce tritium. This involved loading the core not just with uranium, but with cartridges containing a lithium-magnesium alloy. This change was profound. The lithium-magnesium cartridges produced less heat than uranium, altering the temperature distribution in the core. They absorbed neutrons differently, requiring higher overall reactor power to maintain the chain reaction. We now know that the lithium-magnesium alloy was more brittle and had a lower failure temperature than the uranium fuel. This modification meant the reactor was operating in a regime that was experimentally uncharted. The immediate cause of the fire was a phenomenon known as Wigner energy, a defect of graphite moderated reactors that was poorly understood at the time. When neutrons from the fission reaction smash into the graphite moderator, they dislocate carbon atoms from their stable lattice positions. These displaced atoms get stuck in high-energy positions like a spring being compressed. Over time, this stored potential energy, Wigner energy, accumulates in the graphite blocks. If the graphite is heated, the atoms can vibrate enough to snap back into their original low-energy positions. When they do, they release that stored energy as heat. If a large amount of Wigner energy is stored, this release can be self-propagating. The released heat triggers more atoms to snap back, releasing more heat, causing a rapid runaway temperature spike. The operators at Windscale knew about this. In 1952, Pile 1 had experienced a spontaneous, uncontrolled release of Wigner energy while the reactor was shut down, causing a temperature scare. To prevent this, they instituted a procedure called annealing or a Wigner release. Roughly every 6 months, they would deliberately shut down the cooling fans and allow the reactor to self-heat at low power. This controlled heating would trigger the Wigner energy release under supervision, burning it off safely before restarting normal operations. However, as the reactor aged, the graphite degradation worsened. The Wigner energy became harder to release. It required higher temperatures to trigger, and the release became more erratic. By October 1957, the operators were dealing with a cranky machine. On Monday, October 7, 1957, the operators initiated the 9th Wigner release on Pile 1. At 1:03 a.m., the reactor was shut down. The fans were stopped. The control rods were withdrawn slightly to generate nuclear heat. The goal was to raise the graphite temperature to roughly 250 degrees Celsius to trigger the Wigner release. By the afternoon, the thermocouples indicated the release had started. The control rods were inserted to stop the nuclear reaction, allowing the Wigner energy to carry the heat load. The critical flaw in the Windscale instrumentation was the placement of the thermocouples. They were positioned to monitor the reactor during normal full power operation, where the heat distribution is predictable. During a Wigner release, however, the heat distribution is patchy and unpredictable. Pockets of energy can release in corners or edges of the core where no sensors exist. Throughout Tuesday, October 8th, the operators watched the strip chart recorders. The data was confusing. Some thermocouples showed the temperature rising, others showed it falling. The operators, fearing the release was dying out, consulted with the physicists. The consensus was that the annealing had failed to propagate. At 11:05 a.m. on October 8th, the decision was made to apply a second nuclear heating. This involved withdrawing the control rods again and restarting the fission reaction to boost the temperatures. This was the moment the accident happened. Unknown to the operators, parts of the core were not cooling down. They were already extremely hot, but the sensors were not located in those specific channels. By adding nuclear heat to a core that was already undergoing a localized Wigner release, they pushed the fuel cartridges beyond their thermal limits. It is highly probable that one of the lithium-magnesium tritium cartridges failed at this point. The magnesium cladding burst, exposing the uranium or lithium alloy to the air. At these temperatures, uranium oxidizes in air. The oxidation of uranium is exothermic. It creates more heat. The burning fuel ignited the graphite moderator surrounding it. Deep inside Channel 2053, a fire had begun. For the next 24 hours, throughout Wednesday, October 9th, the fire burned silently. The operators were pleased. The instruments showed the core temperature rising, which they interpreted as a successful Wigner release. The release is taking well was the likely sentiment in the control room. In reality, the rise was not Wigner energy, it was combustion. The graphite blocks were catching fire, the flames spreading from channel to channel. Because the cooling fans were off, there was very little air movement to carry smoke to the chimney detectors. The fire consumed the oxygen in the stagnant channels and smoldered, building up intense heat. By Thursday morning, October 10th, the behavior of the pile became impossible to ignore. At 5:40 a.m., the radiation monitors in the stack filter gallery spiked. The needles went off the scale. Initially, the operators assumed a single fuel cartridge had burst, a burst slug. This was a known, albeit messy, occurrence. The standard procedure was to use the scanning gear, a massive robotic nose that moved across the rear face of the reactor, sniffing the air from each channel to locate the leak. When they tried to engage the scanning gear, it jammed. The heat inside the reactor was so intense it had warped the metal structure of the discharge face. The scanner could not move. By 12 p.m., the radioactivity levels on the site roof were rising. The core temperature gauges were climbing past 400 degrees Celsius. Tom Toohey, the deputy general manager, was at home with a family sick with the flu when the call came. "Come at once. Pile number 1 is on fire." Toohey arrived, famously tossing his radiation dosimetry badge onto the desk. "I don't want to know," he implied. He knew he would exceed the lifetime limits that day, and he didn't want the health physics rules to stop him from saving the plant. Toohey and the reactor manager, Tom Hughes, suited up in protective gear and breathing apparatus. They went to the charge face, the front of the reactor. There were inspection plugs, small portholes, through the concrete shield. They unscrewed a plug and peered into the core. We saw to our complete horror, for channels of fuel glowing bright cherry red, Hughes later recounted. It wasn't just a burst cartridge, it was a conflagration. The uranium fuel elements were incandescent. The graphite bricks were glowing. The fire had spread to an estimated 120 channels. The containment of the Windscale fire was a sequence of high-stakes experiments conducted in real time with the fate of northern England in the balance. The first reflex of the control room was to cool the reactor. They switched the main blowers to high speed. This was a logical move for an overheating reactor, but a fatal one for a burning one. The blast of air acted like a blacksmith's bellows. Toohey, watching through the inspection hole, saw the dull, red luminescence turn into a roaring inferno. Blue flames, indicating burning uranium, and yellow flames burning graphite, shot out of the back of the reactor. The roar of the fans masked the sound of the fire, but the thermal readings spiked instantly. Realizing the mistake, Toohey ordered the fan stopped. But the damage was done. The influx of oxygen had intensified the blaze and pushed the temperature towards 1,300 degrees Celsius. The next option was carbon dioxide. The adjacent Calder Hall reactors use CO2 as coolant, so a large tanker was available on site. By the afternoon of October 10th, they rigged hoses and pumped CO2 into the core. The theory was sound. CO2 suffocates fire. The reality was physics. At 1,300 degrees Celsius, the energy was so high that the oxygen was not displaced effectively, or potentially the CO2 stripped oxygen in the chemical chaos of the core. Toohey watched the inspection ports. The flames did not die. The CO2 had failed. Desperate, Toohey organized a team to physically remove the burning fuel. Workers on the charge hoist took long steel scaffolding poles and fed them into the open fuel channels. They tried to ram the burning cartridges out the back of the reactor into the cooling pond. It was brutal physical labor in a high radiation field. Toohey recalled, they jammed solid. The fuel cartridges had melted and swollen, fusing into the graphite channels. When the workers pulled the poles back, they were red hot, the ends dripping with molten uranium. The core was structurally seizing up. They could not push the fire out. By the morning of Friday, October 11th, the fire had been burning for over 48 hours. The biological shield was getting hot to the touch. The concrete was at risk of cracking. If the shield failed, The radiation would be lethal to the personnel. There was only one card left to play: water. Using water on a metal fire is a nightmare scenario for any nuclear engineer. When water hits molten uranium or white-hot graphite, it can split. The oxygen binds to the carbon, releasing hydrogen gas. This creates a hydrogen bubble. If that bubble mixes with air and ignites, it causes a hydrogen explosion. Such an explosion would blow the roof off the containment. The radioactive core would be ejected into the air, raining fallout across the Lake District and potentially reaching Manchester or Liverpool. Toohey and the fire chief consulted. They had no choice. They rigged fire hoses to the top of the reactor face, positioned 2 feet above the flames to create a curtain of water rather than a jet. Toohey ordered the building evacuated. Only he and the fire chief remained on the pile cap. We were quite honestly frightened of the water because we didn't know whether there would be an explosion or not, Toohey testified. At 8:55 a.m., they turned the taps. The water flowed. There was no explosion. They waited. The flames did not go out. The water was turning to steam instantly, but the fire raged on. Toohey then made a counterintuitive genius decision. He realized that even with the fans off, the chimney was creating a natural draft, pulling air through the core and feeding the fire. He ordered the cooling fans shut down completely and the blower house doors closed, effectively blocking the air intake. This stopped the airflow. The water, now flowing at 1,000 gallons per minute, filled the channels. Deprived of oxygen and swamped by water, the fire finally began to die. By 3:10 p.m. on October 12th, the pile was cold. The water was turned off. The battle was won. While Toohey fought the fire, the chimney had been belching smoke for 3 days. The plume drifted southeast across Cumbria, Lancashire, and Yorkshire, and then over the North Sea towards Belgium and Germany. The release contained 20,000 curies of iodine, 131 thyroid hazard, 12,000 TBq of xenon, 133 noble gas, less dangerous, 240 curies of polonium, 210. The presence of polonium, 210, was the dirty secret of the release. Polonium is an alpha emitter, highly carcinogenic if inhaled. It was in the reactor only because the ministry was irradiating bismuth to produce polonium for neutron initiators. This was classified military information. On Saturday, October 12th, scientists analyzing milk from local farms found iodine, 131 levels 6 times the permissible limit. Iodine, 131 falls on grass. Cows eat the grass, the iodine concentrates in the milk. If children drink that milk, the iodine accumulates in their thyroid glands, causing cancer. The government acted swiftly, but quietly. Police woke up farmers in the middle of the night. A ban was placed on the distribution of milk from a 200-square-mile area. Millions of gallons of milk were poured into rivers or the sea. This decisive action prevented a public health catastrophe. It is estimated that this ban reduced the thyroid dose to the population by half. Immediately after the fire, Sir William Penny led a top-secret inquiry. His report was scathing. It blamed the second heating error, the lack of instrumentation, and the poor understanding of Wigner energy. It pointed fingers at the UKEA's organizational failures. When Prime Minister Harold Macmillan read the report, he was alarmed. The timing was terrible. The Soviet Union had just launched Sputnik October 4th, 1957, demonstrating technological superiority. The West was panicked. Simultaneously, Macmillan was lobbying U.S. President Eisenhower to repeal the McMahon Act and share American nuclear secrets. Macmillan knew that if the Americans saw the Penny report, if they saw that the British had built a reactor with inadequate sensors, modified it recklessly for tritium, and then set it on fire through operator error, they would never trust the UK with their technology again. To publish it to the world, especially the Americans, might put in jeopardy our chance of getting Congress to agree to the president's proposal, Macmillan wrote. Macmillan ordered the Penny report locked away. It would not be declassified until 1988. Instead, the government issued a white paper CMND 302 in November 1957. The white paper was a masterpiece of economical truth. It attributed the accident to an error of judgment by the operators, effectively scapegoating the men in the control room while exonerating the designers and politicians who put them there. No mention was made of the polonium release or the specific weapons materials involved. It famously stated, "There is no evidence that this accident has done any significant harm to any person, animal, or property." The strategy worked. The U.S. Congress, unaware of the depth of the failure, amended the Atomic Energy Act in 1958, restoring the special relationship in nuclear defense. Britain got its American blueprints. The price was the truth about Windscale. For decades, the official line remained that no one died. Modern analysis disputes this. Statistical modeling of the radioactive release suggests that the iodine-131 and polonium-210 caused approximately 240 excess cancer cases, of which roughly 100 were fatal. These deaths were not immediate acute radiation syndrome, but statistical deaths, thyroid cancers, and lung cancers appearing years or decades later across the UK and Northern Europe. However, studies of the local population in C-scale have shown mixed results, with some showing no statistically significant excess of thyroid cancer, largely credited to the effectiveness of the milk ban. The filters on the chimneys, Cockcroft's Folly, were the heroes of the story. Post-accident analysis showed that the filters trapped 95% of the particulate matter. Had they not been there, the release would have been 20 times worse. The entire north of England might have faced permanent evacuation. Sir John Cockcroft's paranoia saved the region. Pile 1 remains standing today. It is too dangerous to dismantle quickly. The core still contains 15 tons of melted uranium and thousands of damaged fuel elements. The water used to extinguish the fire caused the graphite to swell and the fuel to corrode. The Windscale fire was a successful failure. It was a failure of design, of understanding, and of political oversight. Yet, it was a success of emergency response. Tom Toohey's bravery prevented a hydrogen explosion. John Cockcroft's foresight prevented widespread contamination. The disaster forced the separation of nuclear regulation from operation, leading to the creation of independent safety inspectorates. It taught the industry that it can happen here, but perhaps its most enduring legacy is the silence. For 30 years, the true story was hidden in a government safe, a testament to the fact that in the atomic age, truth is often the first isotope to decay.